Hi. Welcome to Practical Revit for Structural Engineer, Episode 3. The content of this episode will use the technical terms from the previous episode. If you are not very familiar with the finite element modeling, I recommend visiting the previous episode first. If you are new to Revit and looking for how to begin with basic structural elements such as beam, column, wall, and floor, please check the Autodesk Basic Task for Structural Engineering as per the link provided in the description below. This episode will focus on the modeling of the structural wall in Revit, which is not only for visualization, but also for finite element modeling, and quantities takeoff. In a building, most of the structural wall is reinforced concrete. In the case of structural steel, it would be in the form of a bracing system rather than structural steel wall. Therefore, the formula in this video will be primarily focused on the concrete structure. In case you have the vertical steel plate welded to structural steel member to form some kind of combined structural steel wall, you still can apply the basics of structural wall modeling explained in this video. Because the finite element process for both concrete and structural steel is the same for the linear elastic analysis. Only material properties are different. Why do we need structural wall in the Revit model? It has been explained in the previous episode, that the structural behavior of a thin and long structural element. It could be reasonably estimated using a line element with a proper rigid end zone. Together with most of the professional structural analysis software is able to automatically include the slenderness effect of the line element. Therefore, in this case, modeling with a structural column which includes a line element is superior to modeling with the structural wall which includes shell element. The only exception is, when the structural element is very short, that causing the nonlinear strain distribution, hence, plane section no longer remain plane. Therefore, in this case, modeling using the shell element is better than the line element. And there is no need to consider the slenderness effect for the short wall anyway. The line element could represent the structural behavior of any cross-sections as long as there is no local buckling and plane sections still remain plane. However, since building components such as lift core or stair core cover a much larger area than columns. Not to mention typically there are many openings on the walls. Although it is still possible to mesh the line elements together with proper rigid end zone in order to represent the structural behavior of lift core or stair core. It is a tedious task and most of the time, not worth the time and accuracy loss in comparison with the shell element. In practice, I would recommend modeling lift core or stair core with shell elements for the sake of speed and accuracy. As mentioned earlier, most structural analysis software is lacking the ability to automatically include the slenderness effect in the design feature of shell elements. The structural engineer needs to understand the basic buckling behavior of structure that composed of shell elements before jumping into the Revit model. For any plate subjected to in-plane loading, elastic buckling strength could be determined using this equation. The thinner the plate, the lower the elastic buckling strength. The wider the plate, the lower the elastic buckling strength. The elastic buckling strength of the plate also depends on the boundary condition. The better the boundary condition, the higher the elastic buckling strength. The factor that determines boundary conditions called buckling coefficient. For example, the angle element, or flange of the H-shape section. The buckling coefficient could be estimated using category E, which is simply supported on one edge and free on another. Therefore, the buckling coefficient is 0.425. Another example, the element of box section or web of the H-shape section. The buckling coefficient could be estimated using category C, which is simply supported on both edges. Therefore, the buckling coefficient is 4.0. The angle element or flange of the H-shape section are called an unstiffened element. The element of the box section or web of the H-shape section are called a stiffened element. According to theory, providing the same dimension of plate or wall element. The elastic buckling strength of the stiffened element is almost 10 times higher than that of the unstiffened element. With this knowledge, whenever a structural engineer would like to make the structural wall as thin as possible, try to make it stiffened element. With the elastic buckling knowledge, a structural engineer is now able to identify the buckling coefficient of each wall panel within a lift core or stair core. The buckling strength of the reinforced concrete wall could be determined by this equation. This equation is almost identical to the equation for elastic buckling strength earlier, except that the former Young's modulus now becomes tangent modulus in order to cater to the nonlinear stress-strain behavior of concrete. The buckling coefficient remains the same regardless if it is made of concrete or structural steel. The buckling strength of the reinforced concrete wall determined by the strength of structure just before buckling occurs. Therefore, the cracking behavior of concrete plays no important role here. Tangent modulus could be determined by the slope of the stress-strain curve of concrete at the stress level of a shell element being considering. The stress in the shell element could be determined from the structural analysis under combined load cases such as gravity plus lateral load. The example of how to calculate the buckling strength of the reinforced concrete wall is in the PDF file as per the link provided in the description below. By providing sufficient thickness of shell element, the buckling strength of the concrete wall equal to or higher than the stress obtained from structural analysis. This is a guarantee that there will be no local buckling for all shell elements, hence, the structural engineers could allow the structural analysis software to proceed with the concrete wall design on shell element without the need to consider slenderness effect. However, please keep in mind that, the vanishing of local buckling does not imply that lift core or stair core could be unlimitedly extruded into the sky. The group buckling still needs to be considered for the slender lift core or stair core both during construction and after construction completed. It does not always mean that the structure will be collapse right after local buckling occurs. In many cases, after buckling, the overall structural stiffness will be decreased but could still take some more loads as long as other parts remain stable. The strength of structure that surpasses the buckling strength is called post-buckling strength. In practice, most of the time, it is preferred not to consider post-buckling strength, and just provide the normal buckling strength higher than the loads required. You can create a structural wall model in Revit from the menu, Structure, then Wall. When you already create a wall element, make sure that the structural and the Enable Analytical model have been checked. After the Enable Analytical model has been checked, this will enable Revit to create a finite element for the wall. The finite element for a wall could be seen by setting the visibility option as shown here. Now label the Revit type in order to be used for schedule filtering during quantities take-off. Choose whatever name you like. It could be RC wall, retaining wall, precast wall, whatever. Then from the structural material option, create the physical material property that matches the material you are using. To control the node of the wall element, both base constraint and top constraint parameters shall be as close as the actual level. For example, if the top of the wall is closer to the second floor level than the third floor level, the top constraint parameter shall be assigned to a second floor level, not third floor level. The base offset and top offset parameters could be as per actual in the main Revit model. It is highly recommended that both base offset and top offset parameters shall be set to 0 just before transitioning the Revit model to finite element software. This way, the problem of unintended unconnected nodes will be eliminated. The exception is the spandrel element above the wall opening. One of the offset could be non-zero if the structural analysis software has the auto-constraint function, which will be described later in this video. For the multi-story building, the structural wall model could be either non-splitted or splitted. For me, as the structural designer, since the wall could be changed a lot during design phase, such as, constantly relocation, constantly resizing, and constantly level changing, it is much more convenient and saves a lot of time for me with the non-splitted wall. The structural analysis software such as ETABS will automatically split structural walls at every single floor level during transitioning from Revit to ETABS. Whenever there are several wall panels connected together, it is necessary to review the connectivity quality and make necessary modifications in order to make sure that both visual and structural behavior works as intended. This example shows the issue at the corner due to the two wall panels with a different base or top constraints are connected to each other. The model could be improved for visual by splitting wall panels so that both panels that connected each other have the same base or top constraints. Although I personally prefer the non-splitted wall, but it is necessary to split at this particular spot. Another issue is the unconnected shell element. It could also be fixed by splitting the wall panel so that shell element are connected. In a multi-story building, it is common that there will be an eccentric wall. The eccentric wall could be modeled as actual in the main Revit model. It is the responsibility of the structural engineers to control structural behavior when transitioning the Revit model to the finite element model. Basically, there are two methods to handle the eccentric wall. Method 1. Create a rigid plate to connect the eccentric wall. The rigid plate could be modeled in Revit using a structural floor category. I recommend creating rigid plate in the link file so that the rigid plate will not overlapping with a structural wall. The rigid plate could also be made separately within finite element software so that there is no rigid plate model in the Revit. Assigning the material property requires the proper value that is, neither not too soft to behave like a rigid plate, nor too rigid that risk numerical instability. Actually, there is a method to determine the proper rigid plate's Young modulus so that there is no numerical instability. Unfortunately, that detail is not included in this video. The rule of thumb, that I could give you for a quick assessment, is simply using Young's modulus of rigid plate equal to 1000 times Young's modulus of the structural wall that rigid plate connected to. Although this does not guarantee there is no numerical instability, at least it will be a good start. Method 2. Forced concentric. From the menu, choose Manage, then Structural Setting. From the Analytical Model Setting tab, you can choose the tolerance that just enough to force the previously eccentric wall to become concentric. This method is useful for small eccentricity so that a manual rigid plate is not required. This method also useful when structural engineer chooses the separate their finite element model into the vertical structural system and horizontal structural system. By separating the vertical structural system apart from the horizontal structural system, the inaccuracy of the forced concentric wall could be catered by the horizontal structural system as long as the walls stay within each other. Because typically, the finite element model for the horizontal structural system has been made on each floor, therefore the wall location could be analyzed, as per actual. Whenever the walls located outside each other, then the transfer beam is required. The modeling of the transfer beam in the Revit model properly is not included in this video. In summary, the workflow to export the Revit model to the finite element. First, you have the main Revit model that everything modeled as per actual. The wall can contain offset and eccentric as per actual. Then, just before exporting, you save as your main model to the pre-finite element Revit model. Here, you reset all wall offset to 0 in order to eliminate the unconnected node problem. And choose how will you handle the eccentric wall right here. Finally, you now have a proper finite element model for all of the structural wall. In case, you choose the forced concentric method. And if the tolerance required for structural wall and structural column is different. Or you choose the different methods to handle the eccentric wall and eccentric column differently. You need to separate the pre-finite element Revit model for the structural column apart from pre-finite element Revit model for the structural wall. If you follow the guidelines explained in this video, you can now able to control the structural behavior of the finite element model that exported from Revit model. The Revit model, for other structural elements such as the structural floor, and foundation. It will be included in the next episode, so stay tuned.